It is possible to express any radical expression using rational exponents. Rational exponent, also called a fractional exponent, just has two parts, a numerator and a denominator. Those two parts correspond to different parts of a radical expression. When I say a raised to the power of m over n, my numerator m becomes an exponent on a radical expression, while my denominator n becomes the index of the radical. It's also possible to raise the a to the mth power first and then determine the nth root, but we'll find for our practices that it's almost always going to be easier to determine the nth root of a first and then raise that answer to the power of m. Let's see what this looks like in practice. When I say 27 to the 2/3, what I'm interested in looking at is figuring out what number times itself a certain number of times equals 27. The way to determine that is to first rewrite this using radical form. I'm going to start by taking my base, 27, and making that my radicand. My original denominator of 3 will serve as my index. So here I'm talking about the third root or the cubed root. Then my original numerator 2 will be an exponent to which I will raise that value. The third root of 27, as I've seen before, is 3. 3 to the third power is 27. 3 times 3 times 3. I'm going to take that answer and square it, and my result is 9. 27 to the 2/3 equals 9. Similar process for my other example, negative 32 to the 3/5. Establish my radical and make sure that I include the negative in my radicand since it was in parentheses to begin with. My index is 5, I'm talking about the fifth root, and I'm going to raise this to the power of 3 once I evaluate my radical. The fifth root of negative 32. Now, even though my radicand is negative, because my index is odd, I know that I can do the work. And what times itself 5 times equals negative 32? Well, that's just negative 2. Then I have negative 2 to the third power. Negative 2 times negative 2 times negative 2 is a negative 8. So negative 32 to the 3/5 power equals negative 8. By rewriting my rational exponents as a radical expression, I was able to very easily evaluate each problem. Well, we have definitely gotten through the meat of the lesson. There are just a couple of special cases we want to look at. What happens if I want to write a radical expression using rational exponents, but I seem to be missing either my exponent or the index? It would seem that I would need both pieces to get the numerator and denominator, but sometimes they're not obvious to me right away. Well, whenever I have a radical without an index, the invisible index there is actually a 2, which you know because it's the square root. That's the first radical you ever saw. And when you are dealing with the square root, you know it's the number times itself 2 times that gives you the radicand. So that's how we know that we're going to be using 2 as our missing index. In this case, we could rewrite the square root of x to the third as x to the 3/2. 3 was originally an exponent, so it becomes my numerator. 2 is my index, it becomes my denominator. With this particular problem, since I don't have a number for x, I can't go any further. It's just how we would rewrite it. Similarly, for the fourth root of y, without an exponent visible, I actually could say that my invisible exponent is 1, so that it's possible to rewrite the fourth root of y as y to the 1/4. This happens a lot. Anytime you don't see the exponent, your numerator will become 1 because an invisible exponent is 1. The 4 was my index, it becomes my denominator. The thing to remember here is that an invisible index equals 2, whereas an invisible exponent equals 1. One last final example for this section. Being asked to, without a calculator, determine an approximate value for the following expression: the 10th root of 68 to the 5th power. This seems overwhelming. We're being asked to determine what number times itself 10 times equals 68, and then raise that number to the 5th power. I know I'm going to be working with decimals since it's not going to work out nicely, and without a calculator, I don't want to do that. Fortunately, using rational exponents, we have a solution. I look here at my radical expression and I see 5 as an exponent and 10 as an index. That means that I can rewrite this expression as 68 to some power, that power being a fraction. My exponent of 5 becomes my numerator, and my index of 10 becomes my denominator. Well, when I look at my exponent, it's just a fraction, 5/10, which can actually be reduced. So 68 to the 5/10 would be the same thing as 68 to the 1/2. And when I look at that there, I think I could rewrite that in a simpler radical. So when I take 68 to the 1/2 and rewrite that in radical form, the 68 is my radicand, my index is 2, and my exponent is 1, which I just discussed on the previous page were the values of the invisible index and exponent. All that I'm actually looking for is the square root of 68. What times itself twice equals 68? That's a lot easier to figure out than what we originally thought. Well, we can't do it exactly without a calculator. We do have an ability to think about what number would fit in there. I know that 8 times 8 equals 64. And I know that 9 times 9 equals 81. Therefore, the square root of 68 is going to be between 8 and 9, and it's probably going to be closer to 8 because 68 is closer to 64 than it is to 81. We can take a couple of guesses, but the bottom line is that if you're within a certain range, you'll be all set. I'm going to guess that this is about 8.2, a little bit more than 8. I could certainly use a calculator to check this, and I would encourage you to do that now. But that's just one application of rational exponents to help simplify a really complicated expression.